Quantum computing is one of those topics which is very fascinating and might sound very powerful in the sense, but to be honest, it's also very confusing. People still don't understand what actually quantum computing is. Some would say quantum computing is something that would revolutionize technology altogether, and some would say it is all just hype. My name is Lochan, and I would like to introduce you all to the world of quantum computing. And in this episode, I would like to at least cover what quantum computing is and what it isn't. So before we begin, this is the roadmap that I'll be following for the next few episodes. So in the first two episodes, I'll be going over the quantum foundations, and episode number 3 to 5, I'll be covering the single systems in quantum computing, and episode 6, I'll be covering the inner product and orthonormality. In episode 7, I'll be covering projections and quantum postulates, and in episode 8 to 10, I'll be going over multiple systems in quantum computing. Every computer that we use, from a mobile phone to maybe a laptop, is basically consisting of something known as a bit. A bit is the smallest unit of information, which basically consists of either a zero or a one. So, what exactly it is? So, everything that we use, from a game to or maybe a social media application, is basically just an amalgamation of billions of tiny yes and no's. Just based on a mixture of these yes and no's, all those particular applications and whatever that we're building upon works. Classical computing is something that runs on classical physics, which are majorly written and stated out by Newton and Maxwell. In quantum computing, we don't use bits, but instead we use something known as qubits. The state of a qubit can be in 0 or 1, or it can be in a combination of both 0 and 1. When I say a combination of both 0 and 1, I don't mean that it is both 0 and 1 at the same time matched. This principle is known as superposition, where the state of a particular qubit is obtained by measuring the probabilities of the particular qubit. In classical computing, a bit always has a definite value. It's, as we know, it's always 0 or 1. There's no other possibilities at all. But the definiteness of a qubit only happens after the measurement of the state of qubit. Before we take a measurement of a particular qubit, a qubit can hold multiple outcomes or values to it. But the moment we measure it, it falls down to a single value, either 0 or 1. So the very act of measurement forces a system to a definite state. So till the moment of measurement, a particular qubit can hold multiple values. But the moment when the measurement is done, the value of the particular qubit falls down to a particular state. So this is basically superposition. When it comes to qubits, we write qubits in a different format. We don't write 0 and 1 as it is. We write 0 and 1 into a particular format. So this is known as a ket. So we would say 0 as ket 0 and 1 as ket 1. Okay. So a classical computer usually checks multiple possibilities step by step, so which usually takes a lot of time. But at the same time, quantum computers check this multiple possibilities simultaneously. So when I say simultaneously, it does not mean that a quantum computer checks all the existing possibilities at the same time, but it rather uses a principle called as interference. So in interference, what we do exactly is it amplifies the correct possibilities. And when I say correct possibilities, it means the possibilities that we are expecting. And it cuts down or cancels out the incorrect possibilities that we get. Okay, let's break down some myths about quantum computing and get an understanding of what quantum computers are not. Quantum computers are not just some faster versions of existing computers, and they are not certainly used for activities such as gaming, browsing, or any other activities that we usually do with our regular laptops or computers. These are some specialized machines that are built for solving some particular problems. Problems such as optimization, cryptography, or simulations, for its sake. Some of the big companies that work in building quantum computers are IBM, Google, Rigetti, Microsoft, and there are many more. Okay, now given reality check of the state of quantum computers in the current age, quantum computers that are there today are still very experimental in nature. They cause a lot of noise, they make a lot of errors, and they require a lot of extreme conditions to work efficiently. For example, absolute zero temperature. We can also say that we are in the 1950s equivalent of classical computers. Why should anyone learn quantum now? Like, what is the advantage and the opportunities that we have right now? We are in a very early stage of quantum computing, as we said. It's equivalent of being in the 1950s of computing. Computers back then used to be bulky, they used to be massive, and they used to be very unreliable. But people who understood computing back then have become the architects of the digital world that we know today. Being early does not mean that we get instant rewards, but it means that we have a long-term advantage here. As the field matures, we will have more time to adapt to it. And that I would say is one of the major advantage of starting to learn about quantum computing and its systems earlier. Technology today grows much faster when in comparison to 1950s. We have seen exponential growth in computational power, AI, and in technology. I would say with the right breakthrough, the progress accelerates dramatically. Quantum computing sits at the intersection of physics, mathematics, computer science, and engineering. So the skill gap is real. So the need for people who understand quantum systems is really increasing in the numbers as the time goes. And we know that there are a few people who understand those quantum systems in comparison to people who understand how to build classical softwares. So this is the actual reality of why learning quantum right now is quite advantageous to those who start early. Quantum computing has made us to have a shift in what we understand as computation in altogether. But to understand what actually quantum computing is, we need to understand the physics behind it. And that's exactly where we are going to start in the next episode, where we explore and understand the basics of physics that makes quantum computing work. Thank you.